Last time we start discussing mathematical equation of electrical system. So we start from there, and today we discuss first of all Ohm's law. So if you remember, Ohm's law is V is equal to IR. So normally if we have complex or resistance, or we normally call it as impedance, we can write in terms of Z. So Z is actually a complex impedance. Okay. So when this impedance is only resistance, we represent it by R here, and this is representing for a resistor. Okay. Now again, if we look at the complex resistance, in that case first one is the capacitance. For capacitance, what we have 1 over J. J is for what you say, complex number, and omega C. Okay. Now in that case we have a capacitor. So capacitor actually give lag of 90%, okay, the current. Now the next complex resistance, which is actually due to the impedance inductance, is represented by J omega L. So the element in circuit represented like that. So it is lead 90%. Okay. Now if you remember, if there are two resistors, they are in series, are connected in series, they are 8. So it's equivalent to R1 plus R2. Similarly, if there are two impedance, but in this case these must be real impedance, so you can do the same thing. But if they are resistors that are connected in parallel, now in that case your equivalent is something like 1 over R1 plus 1 over R2 equal to 1 over R equivalent. So this is the representation when they are in parallel. Now next we look at standard voltage divider. Now in standard voltage divider, what it uses has an input voltage here with the resistance connected and the current going is I1 from here. Then if you look, if you want to take out the voltage from here, so this is known as V out, and you have the second resistance also connected with the ground. So if there are two currents, I1 and I2, so because I1 is equal to I2 in this case, okay. Now if I try to write the equation for current, because input voltage is V in here and the next voltage is V out, so we need to take the difference and divide by the resistance in between. So this means that V in minus V out divided by R1 must be equal to, for second we have a ground here and input becomes the V out here, so it becomes V out minus 0 divided by R2. When we solve this equation, it becomes a voltage divider and it can be written as V out divided by V in. After simplification, this equal to R2 divided by R1 plus R2. So this is known as voltage divider. Now next thing, we look some mathematical formulations here. Now the next thing which is important, when we solve these equations, we do have a differential equation. So let's see how we solve differential equation. So now if I look at differential equation here, differential equations, now the generalized form, we can write for differential equation like that. These dots represents the number of differentials, okay, plus u1 y dot, okay, plus a2y is equal to some input that can be written as b1 u dot plus b2 u. So this is a generalized form of differential equation. These dots represent the differential with respect to time. So the class of differential equation that we will do here is ordinary constant coefficient. So class of differential equation, we will look in this course is actually ordinary constant coefficient differential equation, or some people can write as because these are continuous, so for continuous constant coefficient ordinary differential equation. So the question is how we solve this. Now solution, as you know, that can be divided into two parts. First one is known as natural solution, or sometimes we call it as homogeneous. Okay. Now the next one we add is known as forced solution, or sometimes we call it as a particular solution. So these two combine and give us the solution of the differential equation. Now if you look at the first part of the solution, that is known as natural or homogeneous solution. Actually this solution depends upon initial conditions. First point is that this is initial condition, and normally in control system we didn't use the word output, we use the word response. So we call it as this is initial condition response. Okay, so this is the one thing, that this is initial condition. Second is that no external force. These two are very important points, that we put input part equal to 0 and we just work on the initial conditions. And the second one is when we try to solve this, for second one, important point is we start with the system being at rest. Okay, or we can say that there's initial conditions equal to 0. So important thing, whenever we look at the second response, we have to put the initial condition equal to 0. This is 0, right? Now or in other words I can write as I for initial, C for condition equal to 0. And we just look at the response of the input, okay, and I say that I didn't say output, I say response, okay. So you have to familiarize yourself with the control terminologies, and control terminology is the word using response. Now let me look at these solutions one by one. Okay, so first one we are looking is known as homogeneous solution. We call it natural solution because this is due to the initial condition of the system. Now normally the solution has a particular form, and this form is written as y of h for homogeneous. We have a constant a here and s time t, okay. So this is also a constant, okay, and this is a we normally find using initial condition of the system. So this is the form of the solution we assumed. So let's see, if I take the derivative of this one, I can easily write as h dot equal to a s exponential s t, okay. So I take the derivative. Now if you remember, we are looking for solution of this type of differential equation, that is y double dot plus a1 dot plus a2y equal to 0 if I am looking for homogeneous solution, alright. So for that reason I need second derivative, I also need the first derivative. So I take the first derivative for assumed solution. So this is my assumption, okay. I assume this is my solution. Right. Now I take the derivative. Now I have to take the second derivative here. So it becomes a s square exponential st. Now if this is the solution, now I have to, this solution need to satisfy this equation. So if I call it as equation number A, so this solution need to satisfy this equation. So for that reason I have to write equation again here, double dot h because of h plus I am looking for homogeneous solution plus a2y equal to 0. Now I put the values here. So for second derivative I have to put this value. It becomes as square exponential st plus a1 as exponential st plus a2 a exponential st equal to 0. Now if you look here, I can take the common out from here. So what is the common here? Capital A available throughout. Again I can take out exponential est from the equation. So the remaining equation left with is s square plus a1s plus a2 equal to 0. Now this is an algebraic equation. So this is an algebraic equation. So for algebraic equation, why call it equation due to equality? I call it as equation. Now for algebraic equation, you usually found the roots of this equation. Now what are the roots? So assume that roots of this equation, roots are sometimes called solution of this equation. Say because this is the second order, so we have two roots, say s1 and s2. Now from here, because there are two solutions, so my homogeneous solution can be written as yh is equal to a, okay, call it a1, because there are two roots, so I need two of these solutions add up, so it becomes exponential s1t plus a2 exponential s2 of t. So now next task I need, because I know s1 s2 from the above equation, now the next thing left which is unknown is these two. These are unknown. How I find these things? So I use initial conditions. Okay. Now, how I use initial condition assumes that you have initial condition given to you as h of 0 and h dot of 0. So you just plug in, and because you know that y of h is equal to a1 exponential s1t plus a2 exponential s2t. So I can write as h dot equal to a1 s1 exponential s1t plus a2 s2 exponential s2t. Now if I put in initial condition here for 0 for time 0, so okay, this 0 means you have to put t equal to 0, right? Okay, in both cases you have to put t equal to 0. When you put t equal to 0, it becomes h of 0, which is a value, actually a constant, is equal to a1 plus a2. Okay. Similarly, for next case, it becomes h dot of 0 equal to a1 s1 plus a2 s2. Now you have two equations and two unknown. You easily find the solution. So this is the solution when you are solving a homogeneous equation. Okay. Now for a fourth solution, what you do, you actually assume again the input and solve it. Okay. So I am not going in that much detail because this is theoretical part. After some time, we need some transform to simplify our whole scenario. Instead of solving these equations, okay, we use tool to do it. But let's see, let's consider an example here and try to solve that example which has some differential equation. Let's see how we solve that example. Okay. So for assume that now let's consider an example here. Example is that we have a system, mechanical system actually. So this mechanical system has a mass here that is connected with a damper with a coefficient b, and force is applying in this direction, and it is moving with a displacement x. So what we are interested, we are, instead of interesting displacement, here we are interested in velocity of the system. So for velocity, we represent that this velocity is actually x dot, which is represented by b. So means that if I look at the free body diagram, I have a mass here, applied force. So I told you that I am interested more in what you say, velocity. So if you remember the formulation with damper, velocity is multiplied with the damper, and also we have mass. If I you know that if I take the derivative of velocity, it becomes acceleration. So I wrote it. Now if I write the equation, so if I apply the Newton's second law of motion, it becomes F, sum of forces equal to ma, so it becomes F minus BV is equal to mv dot. So this is equation I am getting for this dynamic system. Now here what I am interested in, how we solve this problem. So if I reformulate this equation as mv dot plus bv equal to f, so it becomes a differential equation which has two parts, okay, also has the input in it. So let's see how we solve this equation. And next we try to solve this equation, and because I can divide this equation into two parts, alright. So what we do here, I write the homogeneous part here. The homogeneous part becomes okay. This give me homogeneous solution. Let's put it H here. so that I'm not confused next time. So for H, I told you what is the solution, which we learned from previous example. We know that solution is V of H actually can be equal to some constant A with some exponential st. This is the assumed solution. Okay, this is my assumed solution. Now if I put here, but I need a derivative here, so I wrote here dot becomes a s exponential st. Now if I put these two in this equation, I get a solution. So m dot dot becomes this one, that is a s exponential st. Similar, plus for b times a exponential st is equal to 0. Now because a is constant, I just remove the a and also the exponential. The remaining algebraic equation become ms, okay, plus b equal to 0. Right? So if I have to find the value of s, so from here s is equal to minus b divided by m. Now if I find this root, now I have to put in the solution here, which is v of h is equal to a. Instead of s, I have to put minus b divided by m times t. Now one unknown is still left. This is unknown. Now we assume that initially we need to assume initial condition. Now because this is first order initial condition, so a first order differential equation, we need only one single initial condition to solve this problem. Now we assume that initially at time 0 velocity is represented by v naught. Okay, so when we do that, now we easily write the solution. When we put v naught here, it becomes v naught equal to a exponential minus b by m times 0. So power of exponential with power 0 becomes 1. So this implies that capital A is equal to v naught. Now the solution we get from this is becomes vh equal to v naught exponential minus b by m t. This is the solution we getting. Right? So I wrote solution here so that we clearly look at the solution. It becomes v naught exponential minus b by m t. But this is homogeneous solution. Okay. So this is the first part of the solution. I need the second part as well so that I get the total solution. Now, how we look at the second part of the solution? Before looking that, if I told you to just plot the graph of v of h, so how plot look like? Assume that this is time t and t is starting from 0 to infinity, and on the vertical axis we have vh. Okay, at time t equal to 0 we start from initial condition, that becomes v naught. As time increasing, this will change to, because when I put infinity here it becomes 0, because it becomes infinity power minus infinity, so it can be equal to minus infinity and minus 1. So if I take it to the down denominator, it becomes infinity. So it, when something is divided by infinity, it becomes 0. So as time increases, it reaches to the 0 at infinity. So this is the graph we are getting for exponential minus b by m t, starting with initial condition and b. So the one thing we learned from this graph is that the homogeneous solution or solution that is due to the initial condition is for very small time in the system. So this means that this is also make the transient response of the system. Okay. Now let's look at the second part. Before going to the second part, so the important thing we have to note is that what type of input we are giving to this system, because we represented input in terms of f, so we have to choose the input, then we have to solve the problem. So now question is, how do we add back in the forcing term? Now for this question, we need to look at some inputs that we are using for system analysis. So first one is known as impulse input. Second one is known as step input. Okay. Impulse is for a very small time and also represented by delta of t. Okay. So step input normally represented by u of t, and it start from 0 with a fixed input. Okay. Normally if there is nothing multiplied, its amplitude is 1, and it starts from t equal to 0. So there is another input which is very important and we use for analysis purposes, known as sinusoidal input. Sinusoidal input. So we do normally use this input for frequency analysis because it has frequency in it, and we just want to look at the system this much. Now, whenever we have to look at the input, so assume that for this particular problem, we are taking f of t as a step input, so which has some f naught as the amplitude and t equal to 0. So we assume this is input to the system we are considering here. Now before looking at the force response, so force response is also divided into two parts. So one response is due to the steady state. Second is the transient response. Okay. Now, for steady state, what we say that? We say that all the dynamics die down, or in other words, for steady state, we normally say that our derivatives equal to 0 in the equation. Okay. Now, the equation was, if you remember, m dot plus dv equal to f. First of all, look at the steady state response for steady state response. I have to put v dot equal to 0. I have to put v dot equal to 0. So this implies that we have dvss equal to f naught, because the input is represented by step input. So in this case, vss, ss means steady state. So steady state response equal to f naught divided by v. And this is the steady state response. Now the next response that I discuss with you is known as the transient response, and transient response is the similar one that is due to the homogeneous equation that we solved. So the total response, okay, is equal to steady state response plus a times exponential minus instead of s we calculate b divided by m and t. Okay. So this is equal to the force response, steady state response and transient response. Okay. Now we already calculated steady state response, that is equal to F naught divided by B plus capital A exponential minus B by M T. So what we do not know here is unknown is A. Okay, this is unknown. If you remember last time we calculate unknown using the initial condition, but in force response we said something before. We said that in force response initial conditions are 0. So we have to solve this equation for 0 initial condition. So for this one we have to put initial condition equal to 0. Then we can find this thing. So if I go to next page, I can say that the force response is actually equal to F naught divided by B plus A exponential minus B by M T, and because of the force response we know that initial conditions are 0, so we can say the initial condition is equal to 0. Okay, if initial condition is equal to 0 we have to satisfy this equation, so it becomes 0 equal to F naught divided by B plus A exponential power minus B by M times 0. Okay. If I solve this equation, so from here this implies that F naught divided by B plus A is equal to 0. So from here capital A becomes minus F naught divided by B. Now what is the force response? Now force response becomes F naught divided by B minus F naught divided by B exponential minus B by M T. Okay, this is the force response. Now what is the total response of the system? So I told you that the total response becomes the homogeneous response plus the force response. So total response, homogeneous response was V naught exponential minus B by M T plus, what is force response? I just calculate F naught divided by B, it becomes 1 minus exponential minus B by M. So this is the total response we are getting with input. Now my question is again, if I ask you to plot the force response, this is the force response, okay? How force response look like? So let me plot here. So because we are reaching F naught here, because force response normally start from 0, it will start from 0 and try to reach, start from 0 and try to reach this equation. Okay. So and this reach is become 1 minus exponential minus B by M. Okay. So this is F naught and this is t equal to 0. This is your time t. So this is the force response, okay? I have to write here. Now force response and homogeneous response, when we combine these two, it becomes the response of the system. Okay? Because it becomes F naught divided by B, because this is F naught divided by B. Okay, this is the solution we are getting whenever we try to solve the differential equation. So this means that normally solution depends upon two things. One is the initial condition solution, other is the input you are giving to the system. Now what we do here in control system, so I give you an example why we interested in control system, what is our main objective that we want to achieve here. For example, I give you a very simple example here. For example, this is my car, okay, and I'm driving on a motorway and I want to change the lane. I want to go to the fast lane, okay. So there are different ways that I can go to the fast lane. So first one is that I need to go to somewhere here, okay, so that I reach here. Now there are different ways of doing that. Either I can do very fast maneuvering. When I do very fast maneuvering, so due to inertia of the car, it gives me some resistance. So what happened, it will do something like this, okay, and go like this and this and this and this and this, something like that. So this is very bad way of maneuvering, okay. So you assume if you are driving around 120 kilometer per hour and you do things like this is very dangerous, okay. If your parents is on with you, then then what happened, you know that, okay. After that, the next thing that you can do, you just do this very slowly and do it. But this is also not desirable on the motorway. If you do that, the accident is unavoidable, okay. What we want to do, we want to do it in a way that it is smooth and reach quickly, okay. Now this is there are different responses if you look here. Now because of these responses, we have to choose the specification. So what type of behavior we want from our system, okay, for understanding. Now for this behavior, we have to look at first what is the input, and then we decided how we achieve this. We have to design a controller, but before designing a controller, we need to evaluate the system, okay, analyze the system, then we will move to designing controller to achieve the desired input. Now I told you that normally the response we are very much interested is known as step response. So there are different reasons of that why we use step response. Response means that when we are giving input to the system is step and we observe the output is known as step response. And normally in books it is represented by a one of t, okay, means that it is 1 for all the time, t equal to 0. And the next response we normally do look for initial conditions is known as impulse response. So it is normally used to evaluate the initial conditions. So impulse response, if we do not know the initial condition of the system, we can use the impulse response to find out the initial condition of the system, because it gives the initial condition behavior. So normally we have some impulse at some, for example, t0 time here, okay. So we normally represent it by delta of t0, okay. So it is also known as unit impulse, okay. Normally why we use impulse response, I told you that impulse response actually give us the initial condition of the system. Now if I write here impulse response and see the relation between these two. So first, if this is the input and I say that this is the impulse, normally we represent like that as well with tau and t representation. And we say that if I take the integral of this impulse from 0 to infinity of delta tau d tau, it becomes 1, that is the unit. So means that if I take the integral of impulse responses become the unit step. Okay. Now impulse is that the definition mathematically you already know this, just make a revision, is that there are two parts of it. One is this width and second is this height. Okay. Normally if I represent this height by u naught, width by delta t, so how we represent impulse response? We say that mathematically that as t tends to 0, u naught tends to infinity. So this is the property of impulse. Okay. So from this relation we know that step is equal to actually the integral of impulse. Okay. And second thing, we know that impulse is equal to derivative of step. Okay, remember this thing, because when I take the derivative of a step, it becomes an impulse. Okay, now quickly if we look at our own system, that was, if you remember, mass with a damper, and we are giving force and we are interested in what you say most towards, so we wrote the step response for that, if you remember. And we know that if you want to find the impulse response, what we have to do, we have to take the derivative of the step response of the system. So we already calculate the step response, so we easily calculate the impulse response by taking the derivative of f naught b1 minus exponential minus b by mt. So note here I just wrote the forcing term because impulse is also the input to this. Now when you take the derivative, so what is the result you are getting? This becomes, the first term becomes 0. For second term, if I take the derivative, minus minus becomes plus, so it becomes b divided by m exponential minus b by m t times f naught divided by b. Okay, or I can write quickly as, if I cancel out the, it becomes exponential minus b by m. This is the solution. Okay, for impulse response. Now issue is that this is very easy when we are looking very simple systems, but when we have this is not a good method, we can say that this is a poor method to calculate the impulse response. We have to look some better method. So the better method we will start in next lecture, but we quickly look at is known as block diagram. So block diagram is a better method. So if you look at the mathematical formulation of the system was f divided by m minus b divided by mv. Okay, so I just rewrite the mathematical equation of the model. I just divide the m. Okay, So I need to write this in terms of block diagram. So how we do that? This is the equality. So when you have equality, so this means that you need something that is add up. So if one term is adding, other term is subtracting. So I mentioned this is the subtracting term, this is the addition term. Okay. When they add, what they give us after equality is, what is the output? When these two subtract each other, we get V dot. So we say that the thing we are getting here is V dot. But the problem is we need to apply, what is the input to the system? What is the input to the system is F, okay? So we say that, okay, this is the input F to the system, and if I multiply this by 1 by m, I represent this bit. Now I have to represent this one, but for that we need V, but here we have V naught. How we calculate the V? We need to integrate it. So here what we do here, we do an integration. Okay. When we do that, it becomes V. Now to complete the equation, I need 1 over m, b over 1 over m. So what I do here, I put a block here and write b by m. When it's multiplied and subtracted this will give me V naught. And this is the velocity we are getting. Okay. Now we use this to calculate the impulse response. So for impulse response, assume that we are giving impulse input here represented by F naught. Now when F naught is multiplied by 1 over m, so here what we get here, we get again impulse but with F naught divided by m. Okay, when we come here, because impulse is started at 0, we didn't have the feedback option available at that time. That time feedback is 0, because I told you that initially we start with 0 input. So velocity is initially 0, so there's no feedback is working at that point. So it will jump here, it becomes again same F naught divided by m. Now when I integrate F naught divided by m, what happened? It becomes a step. It becomes a step with F naught divided by m. Okay. Now this means that at time 0 plus, here at 0 plus it becomes F naught divided by m. Okay. Look here. For here, when we look for response at 0 plus time, it becomes F naught divided by m exponential minus 0. So it becomes F naught divided by m. So I am getting the same response here. So we will continue this thing in next lecture, and look here, we can use the impulse response to find out the initial conditions. So impulse response to a system give us the initial condition response. So I stop